So we are going live. Hi, and we're live. Welcome back to another Wednesday open evening at the Institute of Astronomy. I'm here this evening with Dr. Amy Bonsor, who is a Royal Society Dorothy Hodgkin Fellow. We have a bit of a touch and go observing situation. So after the talk, we hope to go live to some live stream stargazing. Our observers are waiting under their telescopes right now and crossing their fingers very hard and trying to see if the clouds will part. So after the talk, we may or may not do some stargazing, but either way, we've got a fantastic talk lined up for you. So Dr. Bonsor is going to be telling us all about how we build the Earth, which is very exciting. So yeah, over to you, Amy.
Yeah, thank you, Matt, for the introduction. Yeah, so hopefully in the next half an hour, I can kind of take us back in history, back beyond the kind of history of our own race, humans, even further back than the history of dinosaurs, for example, on our planet, really to the very beginnings of the planet Earth and how Earth came to be. And hopefully I can tell you about this story that may not be unique to the building of our own planet and may well have occurred many times within our universe. So I thought I'd sort of start out by telling you a little bit about myself. So my name's Amy Bonsor, and I'm an astrophysicist working at the Institute of Astronomy in Cambridge. So this is a nice picture of one of our lovely buildings. And on a nice sunny day, rather than a cold wintry night tonight, this is what you would see. And so kind of as an astrophysicist, I'm studying planets, how planets form, and planets around stars other than our sun. And so on a day-to-day basis, kind of that involves a big mixture of things, from using computers to simulate what's going on in terms of these planetary systems, using a pen and paper to do calculations, to think about and imagine what these other worlds might look like. And then also coming up with questions and theories that we can test by looking at the stars, and then putting together proposals to try and get time on big telescopes, either on Earth or in space, to try and answer some of these questions. In my spare time, I also really love going out in nature. I've got two small daughters and we spend a lot of time in the woods. And this is a lovely picture of Knapwell Woods. This is near to us in Cambridge. And I kind of wanted to start by pointing out like our planet has amazing features on it. If you think of the diversity of things you can see across Earth, from woods to mountains to seas, it's an absolutely incredible and diverse place. So what was it that happened in the history of our planet that enabled us to build all of these places where we have plants, we have animals, we have life thriving across our planet? We also have geology, we have volcanoes, rocks, deserts. So what happened in the history of the planet Earth to make it the way it is today? And so in telling the story of the history of our planet, I thought I'd kind of use the analogy of a person growing up, and thinking of how that baby is first born, grows to be a toddler and a child and a teenager, and then eventually to a fully grown adult, being the kind of state that our planet is in today. So if we think about where our planet was born, well, it was born at the same time as our solar system and our sun, inside of what's known as a big molecular cloud, so a big cool cloud of gas, rather like this one. This is the Eagle Nebula, imaged by Hubble. And what we're seeing is this kind of cool, dense molecular gas that's forming into kind of like clouds that then start to collapse inwards just under gravity. And as they collapse inwards, they can start to heat up. And that process of collapse and heating up is then enough to kind of, or can be enough to give birth to a star. And so stars forming these disks, so any amount of kind of angular momentum, so any little amount of energy that's left within that cloud, as it collapses, it forms down into a plane, a bit like a disk, a bit like a spinning top. And in the center of that, it's feeding this star, so our sun that's being born. So this is an artist's impression here of one of these disks. And right in the middle there, you can see the sun or the star as it's growing, and it's being fed by material from this kind of cool cloud disk of gas now. And so this disk is becoming a kind of planet-forming disk. And we can observe these disks around other stars. So one of the most amazing instruments to do that at the moment is called ALMA. This is the Atacama Large Millimeter Array, and it's situated high in the mountains in Chile. And it observes at what's known as sub-millimeter wavelengths. So this is not quite as long as radio, but almost as long. So And these wavelengths are really, really good for looking at these kind of planet-forming disks. And we've been so fortunate in the last 5 years. We've had so many amazing images of these planet-forming disks, these disks that are forming stars in the center, and then they're going to go on to form the planets within them. And so this is a very famous image of a system that's called HL-Tau. And what you're seeing is there in the middle, you can see where the star is going to be forming. And then what we found, and this was newly discovered with ALMA, was that these disks, they weren't just plain disks, they weren't kind of a sheet of material like a plate, and instead we see rings within this and structure. And those structures are tracing the formation of planets, maybe the formation of bigger planets than our own Earth, more like the gas giants like Jupiter in our solar system. But this is amazing and really exciting that we can actually see what's going on in these really, really early stages of forming these planetary systems. And so to think about what's going on in more detail, let's take this kind of artist's image of one of these planet-forming disks. So we've got the star in the middle, and that star is now starting to grow, and it's starting to be luminous and heat the disk. There's a gap around that star now, and we've got this kind of disk of gas and dust in the middle of that disk. And those are the seeds that are going to form the planets, including our own planet Earth. So one of the things that happens within this disk is that we have these tiny dust particles, and those dust particles can start to grow because they start to hit into each other, and they can start to kind of stick together through collisions, and they can grow bigger and bigger. And so these tiny dust grains, I can kind of see them like being the seeds, or if we're going to go back to our comparison with the human, they're the baby, and they're the tiny little baby that's just been born. It's the first solid material that's going to go on to form our big planet that we're starting off really teeny tiny small. And we're talking about things here that are kind of micrometer in size, tiny dust grains. But those tiny dust grains, as I said, they're all kind of sitting there milling about, and they start to collide with each other. And as they collide, sometimes they do it so slowly and so gently, they just stick onto each other. And then as they do this, then they start to grow, and they become these kind of what we call aggregate dust particles. So they're things that are growing from sticking together many tiny little particles that can grow to become millimeter or centimeter sized dust grains. And so we could see that like our baby now has started to grow into a toddler, and we're no longer a micrometer in size, we're now maybe a millimeter in size, and we're still very, very small. We're still very much in the infancy of that process, but we've started to grow bigger. And this process keeps going. We keep having those collisions, and we keep growing, and then maybe we become a centimeter size, and now we're like a child. And this process is very easy. We can model this process computationally, and we can also do it in the lab. So we have experimental apparatus. There are brilliant groups, for example, in Germany, who have these kind of big tubes where you can mimic the conditions in the side of these planet-forming disks. And you can put into those tubes, you can remove gravity by having something which drops down at the same rate as the acceleration of the Earth, so it's like it's in no gravity. And inside of that, you can put little dust grains, and you can watch them move together, and you can see this going on here, that these two grains, they're kind of moving next to each other, and then they get closer, and then they stick, and they form something bigger, and that keeps happening and happening until you go from something that's micrometer in size to maybe millimeter or centimeter size. And you can imagine those processes could continue, that you could keep growing and growing and getting bigger and bigger until you're a meter in size. But when we get to about a meter in size, we hit a problem. It doesn't work anymore. We can't keep growing. And that problem is that those particles that were about a meter inside, they now can interact with that gas that was all around them that's still there. And that gas causes them to move inwards towards the star. And they do so all of the particles actually were moving into the star, but the meter-sized ones do so faster than anything else, and they do so fast that they don't have time to grow any further before they are engulfed, and they help that feed the star which is growing. So anything that grows to be about a meter inside is going to go in, and it's going to feed that star and make our star grow bigger. But we want to make planets as well as the star. So we need to get bigger than a meter in size, because Earth is a lot bigger than a meter. And we need to get to that next stage and essentially become a teenager. And I always kind of like to think of this as a little bit as many children, teenagers, they kind of, you can be very happy and very, but very apprehensive about growing to be an adult. It's rather like Peter Pan, and you say, no, actually, I'm never going to grow up, and I never want to get bigger, and I'm going to stay a child forever. And that's what happens inside of that protoplanetary disk, that planet-forming disk, is that things grow to become about a meter in size, and then they're never going to get bigger than that. They're going to stay a child forever. That's kind of Peter Pan idea. And so this was a problem for forming planets for quite a long while in the field. And the way to overcome this was people realized that we didn't have to grow from micrometers of centimeter to millimeter to meter and then bigger. Actually, we could just jump straight in there. We could start with our disk of gas and these tiny micrometer sized, or maybe millimeter sized dust particles. And we could suddenly cause something called an instability to happen within that, which enables us to grow straight to form a 10-kilometer sized body. And that instability is called a streaming instability. It's something that happens within the dust and gas. So what I'm showing here is a kind of computer simulation in which you can model these streaming instabilities happening within the dust and gas. And we can model where you would form these then big 10-kilometer bodies that we would call planetesimals, that then are the building blocks of something like Earth. So we're going to skip that size, that stage. We're going to go from micrometer to millimeter to centimeter, maybe, and then we're going to stick straight to being kind of much bigger, tens of kilometers in size. And when we've done that, we can carry on growing quite readily. So those bodies that are tens of kilometers in size, they're no longer coupled to the gas as well. They don't interact with it as much. They can stay where they are. They don't migrate inwards. And what happens is instead they tend to collide with each other. So you form lots and lots of these bodies that are kilometers in size. And you can imagine that you collide together two big footballs that were each a kilometer across. What's going to happen? Something crazy is going to happen. And some of these collisions are really violent. So this is an artist's impression of one of the things that might be going on, whereby we're actually growing, we're getting bigger than tens of kilometers, but at the same time, we're throwing off lots of material and we're changing what's going on in that body and destroying it and growing something bigger. So this last stage of planet formation is really dominated by collisions, and these collisions can be accretional, so they can make you grow, but they can also be really destructive at the same time, and you can lose more material, which you then need to gain again to grow bigger. But eventually you can actually, from all of these collisions, grow big enough to become a planet. And so this is something that we can do on computers, and we've been really lucky within the kind of last decade that actually computers got bigger and bigger, and now we have supercomputers where we can really put in lots and lots and lots of these 10-kilometer sized bodies that would form from the streaming instability and follow all of the collisions between them to really make something that is essentially an Earth-like planet. And so these simulations on the computers, they're tricky to do and they take a long time. So typical simulation might take, for example, a month over 20 cores, for example, so a big computational impact. And so these are the results from one of these simulations. Oh, hopefully it can play. So what we're seeing here is a simulation in which we started with planetesimals, so these building blocks that were about 10 kilometers in size, and we put them in that disk. No, it's not going to play, is it? Okay, and we put them in the disk and we said, well, what's going to happen? They're going to collide together. We're going to watch them. So this is in terms of semi-major axis and something that we called eccentricity, which is how fast, which is how kind of eccentric, how stretched out the orbits of those bodies are. And what happens is that they collide together. When they do that, they grow bigger and bigger, and as they collide together and some of them start to stick, and then eventually by the end of this process enough of them have stuck together that they can start to form some bigger things, which are planets. And what we know happened in the history of our Earth was that one of those collisions right near the end, the last big collision that Earth had, in fact, was so big and so dramatic that it led to the formation of the moon. So people call that body that collided with Earth, the proto-Earth that was still forming, they call that Theia. And this giant impact was big enough and dramatic enough that it disrupted that planet that was forming to become our Earth and made the moon. And the fact that Earth had this giant impact very late in its history is potentially really important to potentially even the existence of us on the planet Earth, but particularly to the formation of a moon system around Earth. And we know that, for example, that Venus and our solar system didn't have such a late giant impact. So just to kind of summarize, we started thinking about how we grow our planet, and we said we start from these tiny micrometer-sized dust particles in the mid-plane of this planet-forming disk, and that these micrometer-sized dust particles are kind of floating around, gently sticking to each other, and they start to grow maybe to millimeter or centimeter size. But then we couldn't get more than meter in size, so instead, at this point, we have this kind of instability where there's a collapse of the disk, and that's called a streaming instability, and that goes straight then to form these bodies that are maybe tens of kilometers in size. And those bodies really then are the building blocks of planets like our Earth, rocky planets. And they go on to collide with each other, sometimes violently, sometimes in a way that they stick and they grow. And eventually, with enough collisions over hundreds of millions of years, you end up with a planet like Earth. And what's amazing to think about is those processes are by no means unique to our planetary system. We observe those planet-forming disks around many, many other stars. And there's nothing special about the physics that we've talked about that couldn't happen around another star. And yet we know that we're here on Earth and that we have animal life and plant life on Earth. And so a big open question at the moment is, well, did something special happen in our history that led to the origin of life on Earth? Or is that something that was typical that happened potentially in lots of other planetary systems around stars other than our sun? And so we can start to think about this, because right now we're discovering planets that are really like Earth around other stars. And we're really lucky to be just getting towards the point where we can detect things that really are the same mass or the same size and radius as Earth. And so an incredible system that was found a few years ago is this TRAPPIST-1 system, which has 7 planets all orbiting on very short, close-in orbits around a star that's a much lower mass than our sun. But most of these planets are about an Earth mass in size, and some of them even have about the same kind of temperature and conditions as our Earth. And what's even more exciting is that within the next decade, we're really going to start to find planets that are like Earth and that actually orbit on year-long orbits around stars that are similar to our sun in mass. And so Plato is a big space mission that's going to be launched in 2026. And the aim of Plato is to detect Earth-like planets on year-long orbits around solar-like stars. And so within a decade, we're really going to be able to start asking that question fully: what is the population of Earths around other stars? And in order to better understand that population of Earths around other stars, we kind of have to understand what it was that happened in forming our system that allowed the origin of life on Earth to have happened. And so the Plato mission aims to detect many, many more planetary systems, and many of these systems will be vastly different to our own solar system, as kind of depicted by the cartoon here, where we can see that some may have a planet that's like Jupiter, but on a much closer orbit. Some may have no big gas giant planets at all. Some may have just very small rocky planets like Earth, but lots and lots of rocky planets like Earth. And some may well be much more like our solar system. So I think we've got very, very exciting decade to come in the study of kind of Earth-like planets around other stars. Yeah, so I'm just going to finish off by kind of leaving you with the question, which is a really open question for our field at the moment, but what led to the origin of life on Earth? And did those same processes happen in the formation of other planets, other Earths around other stars, that might give us clues as to whether or not there's life on other planets around the universe? Cool, so thank you very much for listening.
Wonderful. Thank you so much, Amy. That was super fascinating. Anyone that wants to ask our speaker a question, you can just pop it down there in the YouTube chat. While you're thinking, I think I have a question actually. So I was wondering if I've heard a lot about how James Webb is going to do wonderful things for exoplanet science. Can you maybe talk a little bit about how James Webb will shed some light on some of the things you're talking about today?
Yeah, absolutely. So James Webb is another space mission that's, fingers crossed, going to launch later this year. And it's going to be absolutely amazing for exoplanet science because basically one of the things that it can do is it can start to probe the atmospheres of planets. So at the moment, from the ground, we can start to observe lines in the atmospheres of gas giants, so things like Jupiter, but on much, much closer orbits around the star, whereas James Webb will be able to do that for things that are approaching down to kind of super Earth. So these are things that are maybe 10 times the mass of Earth. And those can start to tell us about, well, if we can find in the atmosphere signatures of things like oxygen or methane or other gases, we can start to understand the geology of some of those planets and really understand what it might be like on the surface of those planets.
Wonderful. Yeah, it's fascinating stuff. It's a very exciting time, right? We have so many nice missions on the horizon to look forward to.
Yeah, absolutely.
Observers, how are the skies looking?
Hello.
Hello, David. How are you doing? How are the night skies looking? Do we have any stars for our audience?
Interestingly, I had Jupiter on the screen a moment ago, but now when I look out, it's completely covered with cloud. I feel I sound like one of those old Patrick Moore programs, you know. Well, I'm sorry, Patrick, it's all clouded in.
The perils of backyard astronomy.
So a moment ago, I had it here for you, just to have a look. Let's push up my exposure and see what we can see through the clouds.
Okay, wonderful. Amy, do you mind if you stop sharing your screen? We'll be able to switch over to the telescope feed.
Yeah, no problem.
Wonderful. Thank you so much.
Hello there, Matt. Can you hear me?
I can. How are you doing, Paul? How's the
sky looking?
I'm
going to repeat exactly what David has just said. A few minutes ago, I had the most marvelous view of Jupiter with the cloud belts and the great red spot and everything for you. But it's like somebody's shut the roof on the stadium at the moment. I can't see a single star. So we've also got Jonathan and hopefully Mick, and we're all at different locations around Cambridge. So I don't know whether those guys have got anything for us.
Well, it's Jonathan here. I can show you the telescope. It's sitting there waiting, looking at clouds at the moment. It's on the table. They are coming and going, but not looking too promising just at the moment, I'm afraid.
Ah, shame. We're getting closer. We've had uninterrupted clouds since the start of the season, and we have some gaps. So we think we're heading in the right direction at least. Maybe next week.
Maybe next week. It was interesting looking at Jupiter through the clouds because it was doing quite a good job of moderating the exposure, and I was getting a really nice image of the planet itself. But sadly, not to be.
It's just reappeared for me.
Oh, go on then, David.
Let me see if I can.
See if you can break our duck.
More going than coming. For a moment, there we are. Let's see if this. This is so frustrating. Where are you? Now, Um,
No,
shall I share? Let me share for a moment.
well,
And
share
see.
your screen, and then if we do get an instantaneous
Have a
glimpse
look,
of
Phil.
it,
Okay, so here we are. You see it there in the centre? Now that's cloud, it's just covered it.
I did see it for about half a second.
Indeed. And if we wait a moment, it might come back. But I, like Paul, a while ago, I was enjoying the view of the belts, and I was just about to be able to pick out where the great red spot was. My telescope is smaller than Paul's, much shorter focal length. So I see less detail than Paul can. But I did have a nice coloured image. And by changing the exposure, I could also see the satellites.
Yeah, I had nice view of the three of the moons as well. I could see Europa, Io, and Ganymede. I think Callisto must be around the back of the planet.
No,
Callisto is well off to the left, I believe. Callisto, Io.
Oh, well, it may well have been out of my field of
there
view.
it is. There it is. You see, I can see it now. It's very frustrating.
There it is.
Can you see that?
Yeah, just.
Believe it or not, that's an 8-second exposure. So we're actually looking through the clouds at this.
Can I share my screen? Because
Sure.
I've now got it. So
Have you come off?
you come off, and I'll see if I can get there before it disappears. Here it comes. Oh, it's faded away. Oh, I was too slow.
Just caught a glimpse.
Just caught it. It was just in this region here. Okay, we'll come back to you.
Let's see if I've got anything.
I literally can't see anything at all when I look into the sky.
If
But,
I
so we're
look
definitely-
out with Mark one eyeball, I can see nothing.
Yeah.
I think it's time to call it a day.
Yeah, I think so, guys.
Yeah, I think this is a swing and a miss. I think we came close. Thank you. You've tried. Thank you very much. We did see our first astronomical object of the season. We saw a glimpse of Jupiter. Yeah, so thank you so much for trying, guys. The clouds have beaten us this time. Yeah, so fingers crossed for next week. So for those of you that are new to the channel, we do these talks every Wednesday evening through the winter. Next week, we're going to have a cosmological talk. We're going to zoom out and talk about the entire universe with Dr. Chandrima Ganguly. So look forward to that and see you next week.